Welcome to Lecture 4, Section 1.2 of the text Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning. This is Dr. Gilbert Eyabi. Today we will be looking at Gaussian elimination and the Gauss-Jordan elimination. Now let's start off by defining a matrix. A matrix is simply a rectangular array. The vertical lines are columns. The horizontal lines are rows. So we say an M by N matrix is a rectangular array that has M rows and N columns. Each entry Aij is a real number. Could be 5, -6, 9/81, 1/2, just real numbers. We call this an M by N matrix. We could have a 2 by 2, a 3 by 3, a 4 by 9. Those are all called matrices. Now let's remind you of something we saw in lectures 2 and 3, elementary row operations. We did see a couple of operations that would produce an equivalent system in previous lectures. Now, since we are dealing with matrices, we're going to transform those statements in matrix terminology and call them elementary row operations. Thus, an elementary row operation on an augmented matrix, which I'm going to define later, produces a new augmented matrix corresponding to the new but equivalent system of linear equations. And elementary row operations are: number 1, interchange two rows, i.e. if you interchange two rows, the system remains the same, the augmented matrix remains the same. If you multiply a row by a non-zero constant, the augmented matrix remains the same, or we say the new augmented matrix is actually equivalent to the former augmented matrix. 3, if you add a multiple of a row to another row, the new augmented matrix is also equivalent to the former augmented matrix. And working backward, the final augmented matrix is actually equivalent to the original system of linear equations. Okay, remember the title of our lecture today is the Gaussian elimination and the Gauss-Jordan elimination. Gaussian elimination is the process that leads to what is known as the row-echelon form, and the Gauss-Jordan elimination is what leads to what is known as the reduced row-echelon form. We would concentrate in this lecture, the first half would concentrate on the row-echelon form. But once we introduce the reduced row-echelon form, we would mostly use this to solve problems in this class. Now, we say a matrix is in row-echelon form if it has the following properties. Number 1, all rows consisting entirely of zeros occur at the bottom of the matrix. So if you are solving and there is a row that consists entirely of zeros, you have to switch and send the row to the bottom. Number 2, each row that does not consist entirely of zeros must have what is known as a row leading 1, i.e. the first non-zero entry has to be a 1. Okay, number 3, for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. I'm going to solve an example in lecture 5 to illustrate this concept. Now let me quickly define what it means for a matrix to be in a reduced row echelon form. That is a matrix that has undergone the Gauss-Jordan elimination process. This is the case when every column that has a row leading one is cleared out. That's the term we would use in this class very often, cleared out. And that means that if there is a row leading one, then all the other elements in that column above and below the row leading one must be zeros. How do we proceed with the Gaussian elimination? First of all, we write the augmented matrix of the system of linear equations. Again, I'll show you how this is done in lecture 5. Secondly, we use elementary row operations to rewrite the augmented matrix in row echelon form. And 3, we write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find the solution. We shall see a couple of examples illustrating this concept. Now, before we close the introduction of Gaussian elimination and the Gauss-Jordan elimination, this lecture on Gaussian elimination and the Gauss-Jordan elimination, let us mention quickly the homogeneous systems of linear equations. Now, we say that a system of linear equations is a homogeneous system if all the constants on the right hand side of the equal sign are zeros. There is something peculiar about this system. You can see that it is always going to be consistent. It would have at least the trivial solution. If x1 equals 0, x2 equals 0, x3 equals 0, xn equals 0, then you can see clearly that this system is going to be satisfied. The equation will be satisfied, the entire system will be satisfied. So every homogeneous system is consistent with at least the trivial solution. But we are obviously more interested in non-trivial solutions. So if a homogeneous system has fewer equations than variables, then it must have an infinite number of solutions, and we are interested in finding those solutions. So what we're going to do in lecture 5 would be to solve a couple of examples. Number 1 would be an example that illustrates Gaussian elimination. Example 2 would reduce a matrix down to a reduced row echelon form. Example 3 would illustrate the idea of infinitely many solutions. Example 4 would lead us to a homogeneous system. And then we might also see a system that has no solution. Thank you very much.